Now I want to consider something else, and that is motion at constant speed around a circle. That's allegedly a circle. So here I have a particle that's going to be moving around at constant speed. How fast is the angle theta changing if the speed of the particle is v? So the particle moves around that circle at speed v. I want to know how fast theta is changing. What's the relationship between the speed v and theta? So the particle moves around the circumference of a circle. I could say that arc length is s. In terms of s, what is the speed? So would it be the change in s over the change in time? Okay, v would be equal to the change in the arc length over the change in time, the derivative of the arc length. Are we good with that? Yeah? How do I express the arc length in terms of the angle theta? Okay, so if this is radius r, then arc length s is equal to r times theta if I use radians for angle, and we will. So ds dt is d by dt of r theta, but r is a constant. We're going to assume that r is a constant. It's going around a circle. So I can pull r out of the derivative. And so the speed is equal to the radius times the time rate of change of the angle theta. Now we often give this derivative, just like we give the symbol v to dx dt or ds dt, we give the symbol omega for the angular velocity. So if the particle is moving around the circle at constant speed, it's also moving at constant angular velocity, and v would be equal to omega times r. So if the speed is constant, then it's not accelerating, right?
Yes, it is. Oh, it is.
If the speed is constant, why is it not true that it's not accelerating? Yeah. The velocity is not constant, but the speed is constant. How can the velocity not be constant? The direction is changing. Velocity is a vector, and so buzz. Who is this? 3? Yeah, okay. I don't want to pinch my fingers. There's method to this madness. Okay, so the position vector, the position of the particle, I can express in terms of r and theta. So the position of the particle, what's the x component in terms of r and theta? Yeah, so I can bring this back down now that I worked so hard to push it up and draw a triangle here. So the x component here, what's the x component in terms of r and theta? Yeah, so I can bring this back down now that I worked so hard to push it up and draw a triangle here. So the x component in terms of r and theta, yeah, so I can bring this back down now that I worked so hard to push it up and draw a triangle here. So the x component here that hypotenuse is length r, the angle here is theta, x is the adjacent, x over r is adjacent over hypotenuse, that's cosine. So I get r cosine theta, and that's in the x direction. And what about the y direction? R sine theta. So now it's child's play. We know how to go from position to velocity. What do I do? Differentiate. V is equal to dr dt. R is a constant, we're assuming, so that comes out. How do I take this derivative? Whose rule do I need? Madame Chain? No, just the chain rule. Okay, so R times what? Hep, hep. Okay, R times negative sine theta times d theta dt. Good. And that's in what direction? X. Is that a constant? Unit vector in the x direction, does that depend on theta or time? No, that's why we like it. It stays put. Okay, and you can do the second one. R is still a constant. We take the derivative of sine, we get cosine. But we have the derivative of theta with respect to time by the chain rule, and we get that. So maybe I'll tidy it up just a little bit. It looks like that thing is an omega. I'll pull the minus sign. Minus omega r times the sine, and plus omega r times the cosine in the y direction. What does that look like? Which way should it be pointing on the figure? Yeah, like that, like the red one. Okay, so let's check it out. Suppose that theta goes to 0. Then this term goes away. And this term goes, the cosine goes to 1, so it would be entirely straight up, right? Is that what you expect from the picture, if theta goes to 0? What about when theta goes to pi over 2? Which way should it be pointing according to the picture? Negative x, right? It should be going backwards. And does that work? At pi over 2? This one goes to 1. So it's negative, pointing in the negative x direction, and that one goes to 0. So that's good. All right, we can play the game again. Take another derivative, the acceleration, dv dt. What happens each time I take a derivative? I get another factor of omega, and the trig does its thing. But I'll work that out. So I have minus omega r. The derivative of sine is cosine. But the chain rule says I need a d theta dt, and that's in the x. Plus omega r. Derivative of cosine is minus sine times d theta dt by the chain rule. So it's time to tidy up. Each one of these is another factor of omega, and both of them are negative now. So we have minus omega squared r cosine theta in the x, minus omega squared r times sine theta in the y. This should annoy you because it's supposed to look a lot like r. I have r cosine theta in the x, r sine theta in the y. That is just r, so I can write the acceleration as minus omega squared times the position vector itself, r. So what should that look like on the graph or on the sketch?
Goes into the...
That means it should be going in the negative radial direction, and that's in. Okay, that's the blue, whoops, that's the blue arrow here. So for a particle that moves around in a circle at constant speed, it is accelerated towards the center. If it weren't accelerated, what would it be doing?
Flying off the circle.
Going in a straight line at constant velocity. So that means that it would have to leave. Okay? So you have to keep bending it towards the center if you want it to go around in a circle. And the faster you go, well, the acceleration goes up as the square of the angular velocity.